Recording.
All right, welcome to chapter 5, everybody. As you can see, this chapter is going to be all about gases. So we have to know how to work with gases in many different areas of science. Those of you who are pre-health, your upper level biology classes are going to need this.
Record.
And pretty much every chemistry class you take is going to need this. So we'll just get started. The first thing to think about is pressure. So what we know as gas pressure is due to the gas molecules striking the walls of the container that it's in. So the gas moves around, it bounces around, it's hitting the walls of the container, and that's what creates pressure. One thing to keep in mind is that pressure overall is force per unit area. So it's the force being applied to the walls of the container as the gas molecules hit it. Gases can be in heterogeneous or homogeneous mixtures. To kind of give you an idea, homogeneous, the components of the mixture are evenly distributed. You can't really see the different parts, whereas a heterogeneous, you could pick out individual parts of the mixture. We need to come to understand units of pressure. So one of the common things to do is to relate everything to 1 atmosphere. And so here you see some conversion factors you'll be able to use. So like 1 atmosphere equals 760 millimeters of mercury. That's an interesting one. Millimeters of mercury is due to old devices. So here you see a barometer, and atmospheric pressure would press on a pole of mercury and it would push the mercury into a column. And then you would read the pressure based off how high the mercury column went in millimeters. But also you see that 1 atmosphere is 760 torr or 1,325 pascals. Pascals is the SI unit for pressure, or 1 atmosphere is 1.01325 bar. So here we go. A gauge on a compressed gas cylinder reads 2,200 psi. Let's express this pressure in atmospheres, megapascals, and torr. Okay, well, part A. Twenty-two hundred psi, and psi is pounds per square inch. So what? That's 14.7 psi for 1 atmosphere. See that psi divides out. And this is going to give us 149.6. Or if we round that off to significant figures, 150 atmospheres. For part B, megapascals. Well, I'm just going to start with the 150 atmospheres that we calculated. Perfectly acceptable to do. Now let's see. Okay, so we want to go from atmospheres to pascals. So from our table above, we see that 1 atmosphere is 101,325 pascals. And then we want to go from pascals to megapascals. And so 1 megapascal, so MPa, as you notice here, that's 10 to the 6th, so 1.0, 10 to the 6 pascals. And when you multiply this up, you're going to get about 15.2 megapascals. Rounding that off for significant figures, we'll get 15 megapascals. So your capital M is mega, where like millipascals would be your little m. All right, in part C, what is this pressure in torr? Well, again, we know that we have 150 atm atmospheres. And then from our table, we see that one atmosphere is 760 torr. And so this is going to end up giving us 114,000 torr. This is probably a place where you want to start using scientific notation. The numbers are getting kind of large. So this would be 1.14 times 10 to the fifth torr. But you want to adjust this for significant figures. That has two significant figures, so we need to adjust the two significant figures. And that's going to be 1.1 times 10 to the fifth torr. So just starting out working on some conversions for different units of pressure. And we'll start going into gas laws. Okay, so Boyle's law is first. So the thing to notice about Boyle's data is notice how all of his relationships is pressure times volume. So here, that column is pressure times volume. It's all the same number. And so for his data show that at constant temperature, the pressure times volume of a gas is going to be a constant. And so we're just going to call that constant K. And so one of the keys here is it's a constant temperature. Now, you'll see eventually that you can solve all these problems just by going straight to the ideal gas law. But here we have Boyle's law. Now, sometimes these laws help us because we can use data to figure out, for example, we can figure out the constant of a specific gas uh, using Boyle's law. So if we take PV equals K and then rearrange this to be V equals K over P or K times 1 over P, what you get here, your V equals K and 1 over P takes the format of Y equals mx plus b, where b equals 0. And so you notice here that, yeah, the line does pass through the 0 point, so b equals 0. And so then for the gas that you're looking at, if you plot volume versus 1 over pressure, you're going to get a line that the slope of which is going to be that constant K for that gas. Now, here's something to think about. The more common form of Boyle's law that most of you might have seen is P1V1 equals P2V2. Well, how does that happen? Okay, so if every combination of P times V equals a constant, this means that condition 1, P1V1, is going to equal, let's see, that'll equal K. Condition 2, P2V2, is going to equal K. Condition 3, pressure 3 times volume 3 will equal K, and so on and so forth, which means that any of these equal each other. If they all equal K, then you could say that pressure 1 times volume 1, condition 1, equals condition 2. And so this is something you can use to solve quite a few problems. So here we go. We have an aerosol can contains 400 milliliters of a compressed gas at 5.2 atmospheres. When all the gas is sprayed into a large plastic bag, the bag inflates to a volume of 2.14 liters. What is the pressure of the gas in the plastic bag? Assume constant temperature. So there we go. There's our contingency for Boyle's law. Okay, so it's asking us for we need to state that it's asking us for pressure two. And then we can say, well, what? P1, 5.2 atmospheres, V1 is 400 milliliters or 0.400 liters. So that's something we know. V2 is 2.14 liters. And you notice I changed V1 to liters because here's something you're going to want to start thinking about. When you're doing calculations, if you're plugging everything into an equation, your units have to match. So I need liters to match liters. When we get to the ideal gas constant, I'll talk about that because I suggest making everything else in the problem, all of your other numbers match the ideal gas constant units. That's just the easiest way to go about it. But here you see it's a single aerosol can. Okay. So whatever's in there is in there. And we're not in a place where temperatures change. Well, it says constant temperature. So we know that uh, so here's things that we know. Now, in that little n is what it's always meant. It's number of moles. Because I'm actually going to start here with the ideal gas law and show you how we can walk pretty much any problem through it. We'll get to the ideal gas law after we get through these individual laws, but still, I'm going to start here. And if you remember, your ideal gas law is pressure times volume in RT, where N is number of moles, R is the ideal gas constant, and T is temperature. I would suggest getting used to turning all of your temperatures into Kelvin. Just do that by practice, and then you won't miss certain things when you're working through exercises. Now, I have to think about what is constant. I know N is constant, T is constant. That means that this nRT, that's going to be our K for this situation. And so since all of that is constant, then from here, I could say, well, every single instance of P times V is going to equal that nRT. So P1 V1 equals that constant equals P2 V2. So that means that P1 V1 equals P2 V2. And again, we can do this because since N and T aren't changing, R is a constant anyway. N times R times T is always going to be the same number in this situation. And so then we can say, well, I want P2, so it's going to be P1 V1 over V2. And I want you doing this algebra before you plug in numbers. Okay, so then what do we have? So like if I was grading an assignment, I better see this. Let's see. 5.20 atmospheres. V1, that's going to be 0.400 liters. Everything is going to be over 2.14 liters. Well, we're in luck here because everything is three significant figures, so our answer will be in three significant figures. When we multiply this out, we get 0.972 atmospheres, and that's going to be our second pressure. Oh, apparently I thought I needed more room. Oh well. Okay. Next up, we have Charles's law, which is another amalgamation of the ideal gas law, kind of introducing a new little symbol to you. So again, the formula for Charles's law is there, but at constant pressure, and there you go, there is the condition for Charles's law. Uh, volume and temperature are proportional to each other. So we could have done that up here too, but I wanted you to see this format first. Because again, the basic formulation of Boyle's law is PV. Actually, we can't do that because proportional to nothing. It's a constant. Anyway, back down here. So this little symbol here means proportional to. So volume is proportional to temperature at constant pressure. And so the way proportionality works is to get an equation you can solve, or one thing equal to another, you need a proportionality constant. So that means that V will equal B times T. B is your constant. So that is called a proportionality constant. Now we can do something similar to Boyle's law, where we are going to rearrange this to get the constant by itself. And so if I divide through by T, V over T is going to equal B, the proportionality constant. Again, to get from proportional to equals, you have to have a proportionality constant. So now that V over T equals a constant, that means every iteration of V over T equals that constant. So V1 over T1 is going to equal V2 over T2, is going to equal V3 over T3, and so on and so forth, and they all equal B. And so that's how we end up here. Boy, I really thought I needed more room than I did, but okay. And this kind of logic is how we end up at this expression for Charles's law. So here, you see proportional to V is proportional to T. Sometimes you're going to see, so let's say, I don't use V and T, but let's say X is proportional to 1 over Y. In mathematical terms, when you see something like this would be called X is inversely proportional to Y. So start working out these mathematical terms in your head. Directly proportional, and because of the 1 over Y, here we have inversely proportional. Okay. So here, a balloon is filled to a volume of 7.0 times 10 to the second milliliters, or that'll be 700 milliliters at a temperature of 20 Celsius. The balloon is then cooled at constant pressure to a temperature of, let's see, 100 Kelvin. What is the final volume of the balloon? So first off, you see I have one temperature in Celsius, one in Kelvin. We're going to need to make these match. And when you're working with gases, always go towards Kelvin. Okay, so we're being asked for volume 2. Okay. Well, we're told that volume 1 is 700 milliliters. T1 is 20 Celsius. T2 So yeah, if you put 10 to the second, I don't care if you write it as 1.0 times 10 to the second or 100. Make sure you keep the decimal point in there, so you go from 3 significant figures to 3 significant figures. So these are things we know. Okay. So again, I'm going to start from PV equals nRT, my ideal gas law, and start applying logic. Okay, so then I'd say, what are all the things that aren't changing? So I look at my ideal gas law. R is a constant. Let's see. Pressure is a constant. Number of moles is a constant. And so what I'm doing is I'm moving things around using algebra to get the things that are changing on one side of the equal side, and then the values that are constant on the other side of the equal sign. So I want V and T on one side, so I'm going to divide through by T, so V over T. Well, let's just do it one step at a time. Okay. And now I'm going to divide through by P to get it to the other side of the equation so that V over T is one side and V and T volume and temperature change. And then NR is, and then, okay, so V over T and NR over P, that's our constant because NR and T are not going to change. And so again, that would be our B in this case. So once again, since we could say V1, if we didn't have the formula for Charles's law, V1 over T1 equals NR over P equals V2 over T2, or V1 over T1 equals V2 over T2. Okay? And so now we have the formula that we need. We need to solve for V2. So I'm going to move that around to get V2 is going to be V1 times T2 over T1. And then from here, I can plug in numbers. Now, our temperatures don't match. So the next thing I want to do is T1 is 20. I want to change this to Kelvin. So you take your Celsius temperature plus 273, and that's going to give us 293 Kelvin. So if you didn't pick it up in chapter 1, every time you change Celsius to Kelvin, you take the Celsius temperature, then you add 273 to it. Now, some people will watch the video and go, say, you're missing a couple decimal places. Yeah, that's fine. I usually pick those up later on in higher level chemistry. Right now, I just, for your first semester of chemistry, I just do 273. So that's what we'll go with. Okay, now we can plug everything in. V2 have my volume 1, temperature 2, 100 Kelvin over temperature 1, 293 Kelvin. When I multiply this all out, I get 239 milliliters. That's Charles's law. Avogadro's law. So here we have another proportionality. In Avogadro's law, volume is proportional to the number of moles. So N. Let's see. Here's our condition for Avogadro's law, constant temperature and pressure. And so once again, because we have a proportionality, we are going to need a proportionality constant. So V is going to equal A times N. So some constant A times the number of moles. Okay, and like we've been doing, let's get that constant by itself. So I divide through by N, and I get V over N equals a constant. And so since every iteration of V over N equals this constant A at constant temperature and pressure, that means that V1 over N1 equals V2 over N2 equals V3 over N3, so on and so forth, and they all equal the constant A. And that is where we get our expression for Avogadro's law. And so, there we go. Okay. Exercise. So here we have a chemical equation. 2NO2 becomes N2O4. If 25 milliliters of NO2 gas is completely converted to N2O4 under the same conditions, what volume will the N2O4 occupy? Now, this one can be a little tricky. You see number of moles, so you might be going, okay, I'm going to have to figure out some molar masses. Not really. Remember, we've been using stoichiometry. Use your stoichiometry. So let's think about this. What are we being asked for? Well, what is volume two? Okay, so what are things we know? Volume one, 25 milliliters. We have constant temperature and pressure, so we're not worried about that. And then N1 equals 2, N2 equals 1. And you notice what I did was I used the coefficients. And so, of course, you always remember there's a 1 when you don't see a coefficient. And those are going to be my numbers for my moles. Okay, and the way I line them up, so if V1 is 25 milliliters, N1 has to be the moles of NO2 or the 2. So that means V2 is for N2O4. And so that means N2 is going to be the 1 mole. And that's the thing with your stoichiometry. This is your NO2 to N2O4 is a 2 to 1 molar ratio. So in this case, your N1, oopsies, N1, N2 is going to be 2 to 1. So yeah, you can use the stoichiometry from the chemical equation. So there's our knowns. And let's use logic, starting with PV equals nRT again. Okay, so we have constant temperature and pressure. So our constants are temperature, R, and pressure. Okay, so let's move everything around to get quantities that change on one side of the equation, quantities that don't change on the other side. So we want quantities that change equals some combination of our constants. So in this case, we'll move to V over N is going to be RT over P. And so RT over P is a constant. So that's okay. So that means now, once again, if we didn't have our expression from up here, so right here, we started with the idea of gas law, and we say, well, so situation one, volume one, number of moles one is going to equal RT over P. But that's also going to equal volume two over number of moles two, which means that volume one over N1 equals volume two over N2. And we're looking for V2, so we're going to multiply through V2. We're going to multiply through by our N2. It's going to be V1, N2 over N1. Now let's simplify this a little bit more before we start plugging in numbers. So I could say V2 is going to be N2 over N1 times V1. I know from my stoichiometry, N1 is 2 and N2 is 1. So this is going to be 1 over 2 V1. So our V2 is just 1/2 V1. And so then from here, we can say V2 is 1/2 or 25.0 milliliters, which means that V2 is going to be 12.5 milliliters. So what we're going to do is we're going to go ahead and stop here so you can kind of review what's going on over the beginning of this chapter. And we will pick it up again tomorrow and see how far we can get. It's kind of a short start, but it'll be good to kind of look at these individual laws and wrap your head around them before we go into the ideal gas law, where we start combining all of the laws into a single equation. All right, see you later.